Okay, so this is a review of chapter 14, which is reaction rates. So reactions take place in a certain amount of time. Sometimes the reactions are going to be slower or faster depending on the conditions of the reaction. So it starts with the idea of collision theory, which is a good follow-up from doing the kinetic molecular theory of gases and all the stuff that we did previously in states of matter in the reviews. But understand that in order for a reaction to occur, the particles have to collide. They have to bump into each other, and certain factors then are going to determine whether or not that collision is actually an effective reaction. Surprisingly, most of them are not. But if there's certain pieces are in place for that collision, then the reaction will occur. So first, what types of things are going to make collisions more likely to occur? Well, one is what phase they're in. Solids can't move, so it's less likely to have a collision with other things. Liquids can move a little more, but solutions and gases are the things that tend to collide most often and have the most mobility of the compounds, and therefore they are going to be the things that tend to have faster reaction rates. So another thing is how much stuff you have, the concentration that you have. The higher the concentration, the more likely you are to have collisions. Another thing is the temperature. The faster the particles are moving, the more likely you are to have collisions. And the last one is a catalyst. Whether you have something that's going to provide another pathway, another energy pathway that's going to encourage that reaction to occur. We also can look at the surface area. So if you have a solid and you grind it down into very, very tiny particles, that's going to be more likely to react faster than a solid that's a big chunk, right? So all of those factors come in. But what it really boils down to in this course is just a few things. We want to look at what's the concentration, because the concentration is going to tell us how much stuff is in there and increase the probability of collisions. The second part of that then is the temperature, how fast are those particles moving, but more importantly with the temperature is not the motion, it's how much energy does the reaction need to occur. What's that energy of reaction? What's that activation energy that's required for the reaction to occur? So the higher the temperature, the more particles have the energy necessary to react. And then the orientation of the particle in space. You know, how is it oriented? Is it going to collide in the way that's most beneficial for this reaction to occur? And then the catalysts do one of two things. One is they can set the orientation and ensure that the particle is in the correct direction for the reaction to be a good one, or the catalyst can provide a different energy pathway through other reactions that can take place with the catalyst involved to lower the overall activation energy of the process. All right, so let's talk about concentration. Higher the concentration, faster the reaction rate. So what we tend to see is concentration and time. If we graph that, we're going to see the concentration and time decrease, right? The concentration will decrease with time, and we know the tangent line to this is your rate, right? The change in concentration with respect to time is your rate. And the rates of the different substances in the reaction are related to each other stoichiometrically. So if you have, you know, CH4 plus 2O2 yields CO2 plus 2H2O, and I know these are all gases, but we can still talk about it in terms of concentration for gases too. You just have to do a little gas law manipulation with the ideal gas law. But regardless, what that means is that this is going to decrease at a certain rate, and this one is going to decrease at twice that rate. And this one over here, the carbon dioxide, then is going to increase at that rate. And this one's going to increase at 2 times that rate. All right, so you can predict what the change is going to be at concentrations of these things over time based on the stoichiometry, right? So if you base it on one, you're going to say that, you know, if I base it on the methane, I'm going to say that the rate of disappearance of methane is half what the rate of disappearance would be of the oxygen, because the oxygen is going to disappear twice as fast. And the rate of appearance of the CO2 is going to be equal to the rate of disappearance of the methane. All right, so that's the first way to think about the rates is what's the rate of disappearance of one substance versus the disappearance of a different one or appearance of another one. So when you find a rate for a rate law based on one of these things, or a rate based on the disappearance or formation of one of these things, you can then use the stoichiometry to apply that to the rest of them. And that's a little quick thing that they tend to stick in there to have you do to see if you understand that the rate of disappearance and rate of appearance of substances is just related to stoichiometry. All right, so that's how we typically look at this. But then what we want to do is we want to find out what the rate law is. We want to be able to have a law that's going to tell us over time what then will be the overall rate of this. And so if we're looking at concentration versus time, then what we're actually starting to look at is what the integrated rate law is. Right? Because the integrated rate law is talking about what's the change in concentration over time. And for this one, if this was linear with concentration and time, then we would know that that's a first order rate law. If I would have to do the natural log of the concentration with respect to time to make it linear, then that's going to be first order. Sorry, concentration versus time by itself, if that was linear, it would be 0th order. Natural log of the concentration versus time is first order. And then if I have to do 1 over the concentration with respect to time and get my curve that way, then that would be second order. And remember, the way to graphically find the rate constant is the rate constant is equal to the slope. Right? So this one, the slope's negative, so the rate constant is going to be minus that value. And this one, the slope is actually positive, so it's just going to be that value. But that gives you a way then to get the rate constant. So we know then that our equation for this is going to be in the y equals mx plus b form. The natural log of the concentration is equal to minus kt plus the natural log of the initial concentration. Right, so somewhere up here is the initial concentration, somewhere down there is the final concentration. That's what those two values represent. And then you get your minus KT in the middle of that. All right, so that's your first order rate law, which they give you right on the periodic table. So most likely, if they're going to ask you a rate law question, it's going to be a first order question because they've already provided you with the equations that you need to use for that. If it ends up being second order, then it's just going to be 1 over the concentration equals KT times 1 over the concentration to start. All right, and that would be a second order situation. So that would be one where even after you did the natural log of the concentration with respect to time, it still had a curve to it. And so then when you do the second order, it should linearize that one out. All right, so there's your integrated rate laws. All right, and once you can figure out what the rate of change is based on these, then you can go apply it to some of those other concepts. But your integrated rate law is going to give you one way to get that equilibrium constant, which then you can go apply to the other rate law, the differential rate law, if you wanted to. And this is specifically for concentration with respect to time. Your half-life comes out of this too. So the half-life for the first order comes out to be 0.693 over K equals the time it takes to go through half of this. Or you could switch that and say 0.693 over the half time is equal to K. So that gives you another use that you can use to calculate for K, or to use K to figure out, well, how long is it going to take time-wise for half of my concentration to disappear? And you can plug that in and figure it out. This is also given to you on the periodic table, so they do not expect you to have that memorized. A lot of times when they do a first order problem that's outside of a typical reaction, they'll go to nuclear. That's maybe the only time that nuclear could possibly show up is when they do a nuclear reaction. They tell you it's first order, and you can use this equation. You can also use it in the other form, which is your concentration is equal to your initial concentration, e to the minus kt, right? So you can do it in the exponential form of that to get your values that way. So, sometimes they'll throw it at you in the exponential form. Just know that these two things are the same. You're just setting it up, and the exponential function is the opposite of the natural log, so you can go figure it out from there. So your first order situation is the one most likely to turn up. All right, so there's the integrated rate law. Now, the integrated rate law can only be done with respect to one reactant and one reactant only. So if you have multiple reactants that are involved in the rate law, it makes it harder to do anything with the integrated rate law, because having two different reactants involved in the integrated rate law makes it really complicated, and that's beyond the course. So a lot of times what we end up using is the differential rate law, which is where you have rate is equal to K times the concentration of A to the, O times B to the P. I'll just, whatever, random variables are up there. So this is the same K value that you would get from the integrated rate law. So if you get it from this one, you could apply it to the integrated. If you get it from the integrated, you could apply it to this one. The rate is related to the rate of disappearance. So when we're talking about the rate of disappearance of one of your, or it could be of appearance, but normally it's disappearance, of one of your reactants in the problem here, that rate can be plugged into here, or that's at least how it's calculated. And so we're trying to figure out what order this is. So remember, the order tells us about how much that one substance actually plays a role in the rate law. So how many of these A particles do I need to actually get through the rate law, the slow step of the rate law, in order to get my reaction going? And how many of these do I need? Remember that the orders are not going to be related to the stoichiometry in all cases. So do not expect the stoichiometry to give you the values for O and P right out. They're going to give it to you through lab data. So if I pull some data out of a book, they give you some experiments. In one, A is 0.100, B is also 0.100, and the next reaction, A is 0.100 and B is 0.200, and in the next one, A is 0.200 and B is 0.100. And then they give you the rate for those. So the method of initial rate is a way of saying, okay, when we start, here's what the initial rate is. So they give you that, and they say this one's 4 times 10 to the minus 5. And the next one is 4 times 10 to the minus 5. And the last one is 16 times 10 to the minus 5. So this is experiment number 1, 2, and 3. So the easiest way to do this is to find two experiments where we kept one of the concentrations constant. They don't have to do it for both reactants. They might only give it to you for one and make you do some other calculations for the other one. But you should at least be able to find a situation where one of your reactants is held constant. And remember, this doesn't just have to be two. This could be one reactant. It could be two reactants. It could be three reactants. You can still figure it out based on all of those, as long as the other concentrations are held constant. So if I go and divide experiment 1 by experiment 2, I'm going to have 4 times 10 to the minus 5 divided by 4 times 10 to the minus 5. And on the other side, right, because they were both the same. And on the other side, I have K over K. And I have 0.100A, 0.100B, 0.100A, 0.200B. And those are raised to the 0 or the O power, and these are raised to the P power. I guess O is not a good letter to use, right? Usually they use M and N or something like that. So when I go and calculate this, this cancels out to 1. My K's cancel out. This cancels out. So I'm left with 0.1 over 0.2 to the P is equal to 1. And so therefore P is going to be equal to 0. So B, now I know, is going to be 0th order. Oh, that's a disaster. I can't believe I used an O. What am I doing? I'm going to call this Q now. I'm going to change it because that's just stupid of me. So remember, don't use O. There you go. All right, so now we know that B is 0th order. So I go back and I do the same for where B's held constant and A's changed. And so I get 4 times 10 to the minus 5th equals K times 0.100 times 0.100. And now this is to the Q power, but we know that B is to the 0 power. And then I'm going to divide that by 16 times 10 to the minus 5 is equal to K times 0.200 to the Q times 0.100 to the O, or 0 power, sorry. And so those cancel, or if I had to do the math, I could do that now that I know it's the 0th power, so really both of these are 1s. The K cancels, so I get 1 over 4 equals 1 over 2 to the Q. And so that means Q has to be equal to 2. And so now I know that my rate law is going to be A to the 2, B to the 0. Or I could rewrite that as rate is equal to K, A to the 2, and leave it at that. So this is good. Now I have one reactant that's involved that I know is second order, so I can use the second order rate law to solve anything after this. And the other thing I can do with this now is I can take any of these situations, experimental situations, and take the rate and plug in the concentration of A and go and solve for my value for K. So if I say 4 times 10 to the negative 5th is equal to K times 0.100 molar squared, right? So if I go and do the math on that, I really didn't need a calculator for this, but 4 times 10 to the negative 5th equals K times 0.01 molar squared. And so, and the rate constant is usually in, or sorry, the rate is usually in change in molarity per second, right? So this is molarity per second. And then when I divide 4 times 10 to the negative 5th times the 0.01, I get 4 times 10 to the negative 3rd, and I get the molarity squared on the bottom, molarity on top. So I actually end up with molarity on the bottom and seconds on the bottom. So that would be my rate constant now for that equation. So my rate law then would be rate is equal to 4 times 10 to the minus 3rd, molarity to the negative 1, seconds to the negative 1, times A squared, B to the 0 if you needed to, but you could just leave it off. So I could put my value in for K now. All right, so that's how you work through the differential rate law. Okay, so the next part of this then is to start to talk about all of the collision factors that go into this. So this is the Arrhenius equation. The Arrhenius equation is useful for us to start to talk about our activation energy and its relationship to the rate constant. So here's my rate constant. There's my activation energy. They're both in this equation. Natural log of A has to do with the frequency of collisions and the probability of those collisions having the correct orientation. So that's all factored in with this A value. So that's something that can be experimentally determined or experimentally predicted or all of that. But that's what that A value is giving us is, okay, how many collisions will there be and how many of those collisions are actually going to be with the correct orientation and therefore effective. And then we can relate that by itself to, okay, how is that affected by the activation energy and therefore give us our rate constant. Typically, we don't look at the Arrhenius equation this way because it's not very useful to us because it's hard for us to calculate what the A value is. So normally we look at the Arrhenius equation in the K1 over K2. Natural log of K1 over K2. And then we do it this way because now this is the graphical one where we can say, okay, natural log of K is here, 1 over T is here. We get a negative slope here, and the value of this slope is going to give us negative EA over R. Okay, so we can use that then to calculate the activation energy from the graphical data that's given to us. So you can plug in any two temperatures, you can plug in your K values under those different conditions, and then you'll get your equilibrium expression from that. Or sorry, that's not what I meant to say at all. I meant to say your activation energy from that. All right, so what's the purpose of this? Well, the activation energy comes back to, all right, how many collisions are actually going to be able to overcome that energy of the reaction? So first of all, we go back to our Boltzmann distribution, and we know that there's a certain number of particles that have all these different energy values, right? And so somewhere is a value where, okay, if this is my activation energy, then only those particles above here have the activation energy necessary in order to react. And that's why this is what temperature is all about, right? Temperature is not about the frequency of collisions and increasing that because now you have more particles moving faster. Temperature is about crossing this activation energy value and getting more particles in this area above the activation energy so that we have more particles that have that energy necessary to make the reaction occur. Because if we heat them up, we know that this Boltzmann distribution stretches. And now we have a lot more particles over here with the necessary activation energy, actually a big number of increased amount of particles. And that's why temperature has such a huge effect. A little bit of a temperature change can statistically have huge percentage changes in the number of particles that therefore have the activation energy and are able to react. So that's kind of what we're calculating here. This activation energy never changes for a typical reaction. So when we start talking about activation energies, you have to understand that you can't really change the activation energy without a catalyst. That's the only method you have to change the activation energy. That activation energy value is constant. You have to change the conditions of the reaction in order to guarantee that more or less particles can cross that activation energy. All right, so now we have what this activation energy is and what the temperature effect has on that and how that's going to affect your equilibrium constant. And that's why temperature plays such a big role. Sorry, here it's your rate constant. I'm so excited to do equilibrium. That's my problem here, right? But the more particles that have the necessary activation energy is going to cause your rate to increase. And as your rate increases, that's going to change your rate constant. And therefore, we're going to see a much faster reaction occurring. So the one thing we didn't get into here is reaction mechanisms, right? So now we know, I know this one's a really long one. All right, we know there's many steps for a reaction to occur. So when we look, we can talk about our energy on the Y and time on the X, and we can look at our energy changes as the reaction occurs. And we can get something that looks like this. Right, so now we know that we're starting here and we're ending here. Right, and that's higher by a little bit, so we know that our delta H equals a positive. So that's the first thing, is we can tie that in with the thermodynamics and talk about that this is an endothermic reaction overall. The second thing we have to recognize is that each of these then requires a certain activation energy to get there. Right, there's a certain activation energy to get over that first hump and a certain activation energy to get over the second hump. But the overall activation energy is from the highest point down to here. So that's the one we're going to cause call our activation energy for the overall reaction, because we're not seeing this stuff happen in the middle. These values up here are your states where you have radicals or parts of molecules or really energized things going on. These are temporary states where atoms can be by themselves, or pairs of electrons can be broken, so you have unpaired electrons and all of those sorts of things. So there's all sorts of different names they come for that, that they can give you for that. But they are not going to be long-lived significant states. And we consider these things down here, the values down here, these are your intermediates. The intermediates are the things that are produced in the middle that it seems like a reaction's done, but then those things are used up again in the next reaction. So intermediates will actually show up in your rate laws. These other things up here will not. The transition states will not, because it's literally what they call it, the transition state. It's transitioning from where you started to that intermediate, or these intermediates to that one, or whatever. So the intermediates are actually going to show up in your rate laws. So what is important about this is, let me actually find one that we can use. Okay, so here's a sample mechanism. You have 2A plus 2B yields 2AB. And this F over here means it's a fast step. So that means that as quickly as these two things are in there, they're going to be making that. That AB then is going to come down here and react with another A to make C. This is our slow step. So what that's telling us is that our whole rate is dependent upon how long it's going to take us to make C, right? Because C is needed in the third step. So if it takes me a really long time to make C, then our overall rate of the reaction is also going to be slow. So the quicker we can make C, the quicker our overall rate is. But that's the one that determines how long it's going to take. Because once C is made, C goes down, boom, used, and it's gone, right? So there's my slow step. That's what I consider my rate determining step, because how fast I produce C is going to determine the whole thing. And this actually matches kind of what's over here, right? Because my second step, my first step, gets up to here. It's got a fairly high activation energy, and then it drops to my intermediate, and then it jumps up to here. This is my highest activation energy at this point. And since that's where my highest activation energy is, that's going to be my slowest step. Wherever you find the highest activation energy is always the slowest step. So now that I know that, I can go figure out two things. First, what's my whole balanced equation? So let's start looking at intermediates. These are the things that are not going to appear in the balanced equation. So my intermediates are the things I produce but then use up. So my intermediates are A, B, and C. Because as I produce the AB, the two ABs here, one gets used up there, one gets used up there. So it's produced and then used up. These intermediates are produced and then used up, right? And my other intermediate is C, because I produce it here and then I use it up over there. So my balanced equation would be based on what's left here. It would be 3A plus 2B yields D. That's my balanced equation. And so my rate law then is based on all the things I need to get through my slow step. So my rate law in this case would actually be equal to my balanced equation. K times A cubed B squared. Right? Because my last reaction was all intermediates. So it didn't matter that those were my reactants. My reactants were all up here. It was necessary to get through the slow step to use all of that. So how would this change? Well, what if my slow step was the first step? What if making the AB was everything else, was dependent on everything else, which actually would probably make more sense based on what I wrote on the board anyway. Well, how would that change? Well, that wouldn't change the balanced equation at all, because the balanced equation still requires 3 A's to react with 2 B's to make this D, right? But what it will change is my rate law, because if this is my fast step and that's my slow step, then I don't need that other A to be in my rate law. Now my rate law is going to be a squared v squared, because that's what I need to get through the first step, which happens to be the slow step. Everything after that is inconsequential to my rate. So that's how you can use the different mechanism steps to figure out what your rate law is and what your balanced equation is. That's how you can compare these mechanism steps with a graph, and recognizing that your slowest step is going to be the one that's going to require the highest activation energy from the start, right? It's not the activation energy from the last set of intermediates. It's where's the highest activation energy from where I started. That's going to give me an indication of what my slowest step is. And if we were to look in reverse, then that's still going to be my slowest step, the second one, according to this graph, because going backwards from here to there, that's still the highest peak. Okay, so I think that covers everything. Rate laws, catalysis and using catalysts is not something that they care too much about. Just understand that what the catalysts do is they lower what your activation energy is to get through a reaction. And the reason why they do that is because they'll change what's happening in the mechanism, and they'll give you a different path. It does not change the starting and ending. The catalyst will not change your delta H at all, right? But it will speed up your reaction because you'll have more particles then, according to Boltzmann, right? If you change the number of particles and energy, and you have this, right? Changing the temperature, we said, flattens out this curve. So if our activation energy is right here, we'd have to change the temperature to get more particles over here. But if you add a catalyst to it, that might lower our activation energy. And when that lowers the activation energy, that's going to automatically have more particles. That many more particles now are going to be beyond the activation energy for the reaction to occur. And so now the reaction can happen quicker. So that's typically what we say the catalyst does, is it lowers the activation energy, it will modify the mechanism, and that's why reactions happen faster, because now it's easier for more particles to go through that reaction. And that's really the end of the catalyst discussion. So at this point, I think we've covered everything rates, and I know this is a long presentation, but we're out.